Okay, so today we're going to talk a little bit more about the digital multimeter. We've already talked a little bit about it. We've used it in some of our labs. We've used some of the basic functions. Today we're going to talk about some of the more advanced functions. We're going to talk about the way that we can use it to measure frequency, capacitance, and high current. Okay? So I'm going to first talk a little bit about what each of these things is, and then during the lab preview I'll show you how to use the meter to actually measure each one of those things. Okay? So this is going to be it should not take too long to get through this stuff. We're also going to have a visit from Professor Gary George this morning. He's going to be observing me as part of a yearly evaluation. So he'll just be sitting in and watching the lecture, and then at the end of the lecture he'll probably have a sheet, an evaluation sheet for you guys to fill out. So I will step out while he does that, and then you guys can fill that out. Okay? So let's start by talking a little bit about frequency. We've already discussed this a little bit, but let's go through it again and talk a little bit about some of the definitions that go along with frequency. So frequency is a term that applies to a signal or a phenomenon that repeats over and over and over again. Okay? And frequency is really how quickly that signal repeats. Okay? So if you're talking about a sine wave, for instance, the frequency is how many times that sine wave occurs in 1 second. Okay? The most standard unit of frequency is hertz. And that's abbreviated Hz. So if this signal repeats 1 time every second, that's a frequency of 1 hertz. If it repeats 10 times every second, that's a frequency of 10 hertz. Okay? So that is the most standard unit of frequency in electronics. But there are other units of frequency that apply to other things. So for instance, if you were talking about a car motor and how often the car motor turns, then you might talk about RPM, right? You guys know what RPM stands for?
Revolutions per minute.
Yeah, revolutions per minute, exactly. So in this case, the thing that's repeating is a revolution, right? 1 complete cycle of the motor, and the unit of time is minutes. So if you're talking about 3,000 RPM, that means that the motor is turning 3,000 times every minute. Okay, so that's another unit of frequency. So there are other units of frequency as well, but in electronics, hertz is the most common. And again, that's cycles per second. And we said that there is another term which goes along with frequency, which is often used at the same time, and that is period. So the period is the duration of 1 complete cycle. So if it takes 1 second for a cycle to complete, then the period is 1 second. If it takes 5 seconds for the cycle to complete, then the period is 5 seconds. So the period and the frequency are related to each other. So we say that the period is 1 over the frequency. And similarly, the frequency is 1 over the period. Okay? So I think we've discussed this already, but just I wanted to make sure that we have that clearly in mind when we're talking about frequency today. Okay? Any questions about that? All right. So that's really what we want to say about frequency. So let's talk a little bit about capacitance. Capacitance is a measure of basically how much, or it's a measure that is used with capacitors, okay? Not surprisingly, the names sound very similar. But we haven't really talked about capacitors yet. Okay? We're going to have a whole lecture a little bit later on that discusses capacitors and inductors. So we're going to talk a lot more about it later on, but I want to tell you a little bit about capacitors now so that you have some idea of what we're measuring when we measure capacitance. Okay? So first of all, let's talk about what a capacitor is. Okay? So fundamentally, a capacitor is just two plates of metal that are close to each other but not touching, and they are separated by a layer of insulating material called a dielectric. Okay? So you might ask, well, what's so interesting about two pieces of metal close to each other? Well, what we do is that we attach wires to the two sides, and then we can put charges on these plates. And basically, this capacitor can hold a charge. So it can store the electricity. And we can store the electricity there for long periods of time if we want to, or just very brief periods of time, depending on the application. But the basic purpose of a capacitor is to store electricity. Okay? So let's talk a little bit about how it does that. Basically, if you put a positive voltage over here and a negative voltage over here, what happens is that you end up with positive charges. The little positive charges flow from your positive source, and they build up on this plate of the capacitor. And electric charges work kind of like little magnets. Okay? Basically, opposites attract each other. So when you have a whole bunch of positive charges over here, they attract negative charges from the other side. And they repel the positive charges from the other side. So the positive charges on the other side leave that capacitor. Okay? So you get positive charges flowing in from the left. They build up, they attract the negative charges over on the right, and then the positive charges flow away. So now if you take away your voltage source, so you don't have any more charges flowing in or out, you still have the charges that are already there. Okay? They're still built up, they're still attracting each other. So you still have this stored electric energy in the capacitor. Okay? And that energy will sit there for a long, long time, right? You can have these capacitors store energy for days or weeks or even years on some of them. So the capacitor really stores up the energy. That's its main purpose. Yeah?
What would be contributing factors to the length of time and how much a capacitor can hold?
Yeah, I'm glad you asked.
Material?
Yeah, so about the length of time, what happens is that all capacitors have a little bit of leakage where charges can jump from one side to the other, right? They're attracted to each other, so some of the charges actually manage to jump across this gap. and that's called leakage. So the better the insulator you have in the middle, the less leakage you have and the more time the capacitor can hold the charge. Okay? Now, in terms of the factors that determine how much capacitance you actually have, there are three main things that contribute to that. So the first is the size of the plates. So this kind of makes sense, right? If you have really big plates, then they can hold a lot of charge. If you have really tiny plates, then they don't hold very much charge. Okay, so if you have, the bigger the plates are, the more capacitance you have in general. The next thing is the distance between the plates. Okay, so you know, if you've ever played with magnets, the closer they get to each other, the harder they pull on each other, right? It works the same way with the electric charges. If they're really close to each other, they're pulling really hard. So these positive charges can attract a lot of negative charges if they're really close to each other. If they're farther away, then they're pulling a little bit, but not nearly as much. So the closer the plates are together, the more capacitance the device can have. Okay? As they're farther apart, they store, or they have less capacitance. And then the third factor which contributes to the capacitance is the dielectric material. Different materials have different properties, and so they result in different capacitances. Yeah?
Does the material, what the plates are made of, does that matter?
Not really. Maybe a little bit, but not very much. Yeah.
My experience with capacitors is in stereo equipment, and everyone I've ever seen has been cylindrical.
Right.
Are there still just two flat plates in there, or are they doing some type of where they are rounded? Or?
No, that's a great question. So what happens when you're talking about those cylindrical capacitors, those are usually electrolytic capacitors. And what happens is that the way that those are made is that you start with two long pieces of aluminum foil, essentially, and then you put layers of thin insulating material between them, almost like wax paper or something like that. And then you roll them up.
And the wax paper is the dielectric.
Right. So it's not actually wax paper, but it looks very much like it. It feels like it. So exactly. So that's the dielectric.
So it's two plates, but they're wrapped around each other.
Yeah. So they're still close to each other in proximity, but they're just wrapped up. Yeah. So that's electrolytic capacitors are a very common type, but there are also small capacitors which are often made out of ceramic, which are just sort of flat plates right next to each other. Yeah.
So what's the difference between capacitors and batteries?
Yeah, so that's a great question, right? So capacitors and batteries both store electric energy, right? And both of them, well, they're rechargeable batteries, so you can put electric energy back into that. So the difference is that it is basically the way that the energy is stored. With batteries, energy is stored in a chemical reaction. So batteries are made of plates of metal, typically. I mean, there's lots of different types of batteries, but a typical kind of battery is made out of plates of metal that are submerged in acid or some other type of conducting liquid. And this acid reacts with the metal and it releases, it creates a voltage between the plates. So the more the acid reacts with the metal, the more energy it releases. And when you recharge them, you're doing the opposite. You're causing the opposite reaction to happen. So the metal is, I'm not exactly sure about the chemical reaction, exactly what's going on, but the metal is releasing energy into the battery when you are recharging them, and it's drawing energy out of the reaction when you're discharging them, when you're using them. So it's fundamentally a chemical reaction that's taking place. Whereas with the capacitors, it's just this this charge attracting opposite charge, which is holding the energy.
So, I mean, since they both kind of do the same thing, why would you use one instead of the other in certain circumstances?
Right. Well, so capacitors, for instance, can charge and discharge very, very quickly. So they can be used for certain applications where batteries would not work. So for instance, like you were talking about in stereo equipment, capacitors are often used in filtering applications where they allow high frequency alternating signals to pass through them, where they block out low frequency signals. So they can charge and discharge much more quickly. Batteries typically have been able to hold more energy in a small package. Another way of saying that is they have more energy density. You can get more energy in a per pound or per square foot or whatever in batteries. But that is changing also. Recently, like in the last 10 years, companies have started to develop supercapacitors that can store large amounts of energy. And those are just now coming onto the market and becoming available. So those are starting to compete with batteries in certain areas, where you can store up a lot of energy in a supercapacitor and then use that in place of a battery. Yeah. Other questions? Yeah.
Is there a formula to know how much is stored?
In a capacitor? Yes. There is, and I don't know that off the top of my head, but yes, there is one, and it relates primarily to these three things. And we'll talk more about that in a later lecture when we actually make our own capacitors.
Oh,
Okay.
nice.
Yeah. So yeah,
Sweet.
yeah, it should be fun. We're going to make our own capacitors and our own inductors a little bit later on. So yeah. Other questions? Yeah.
My understanding of like application with capacitors is it kind of provides a backup or an assist to your power supply, whether it be a battery or from the wall, as other components are drawing too much current. This backs up with the power supply. Is that
Right. So that is one typical application for capacitors, and we saw that when we were looking at our fiber optic receivers. Right. They had a capacitor in parallel with the battery. So the battery was there to provide most of the energy, like you said, but then there was a capacitor over here also. So the capacitor acted sort of like a spare reservoir for the power.
more consistent?
That's exactly right. Yeah. So the battery could charge up the capacitor when not much energy was being used, but then when there was a big draw of energy, the rest of the circuit could pull some of that energy out of the capacitor, and like you said, the voltage stays more constant that way. So
Is it voltage or current?
well, both. Well, it's the voltage that's staying constant, right? So you had about a 9-volt source here. So this charges up the capacitor to 9 volts, and then when the rest of the circuit tries to draw a lot of current, that brings the voltage down a little bit, and it draws some of the energy out of the capacitor to supply that extra current. And then when less current is needed, the battery charges the capacitor back up again, and it's ready to be used the next time. So that's one application for capacitors, but there are others as well. So when we looked at the fiber optic receiver, there were some capacitors that were used around the speaker, and those were used for filtering. So they allowed the AC signal to pass through, but they blocked out the DC. So so we had more circuit here, and then we had our speaker. And we had the signal coming into the speaker, but we had a capacitor in series with that speaker. So this allows the AC signal to pass through, but it blocks out the DC signal. And that's good, because the AC signal is what we want. The AC signal is the sound signal. When we listen to sound, our ears can detect frequencies in the range between approximately 20 hertz and 20 kilohertz. So those are all AC signals. So we want those signals to go to our speaker. But we want to block out DC signals. DC is direct current, it's just constant voltage. And if we had a constant voltage going to our speaker, that would be bad for a couple of reasons. First of all, it would be, remember, the speaker is just essentially a coil of wire, okay? So if we had a DC signal on a coil of wire, that would just be, there would be very little resistance, and that signal would be pushing a lot of current through that wire. So the wire would be heating up, and it could damage the speaker, and also be draining our battery. So we want to block out DC signals from our speaker. So putting the capacitor here acts like a filter and allows the AC to go through, but blocks out the DC signal. So that's another use for capacitors. And there are other uses as well, but those are a couple of typical examples. Yeah?
How does it stop the DC from going through, but allowing the AC to?
Yeah, okay, so what happens is that so like I said, the capacitors are just these two plates of metal, right? Mm-hmm. So if you have 9 volts over here, say, and it's just a constant 9 volts, what that does is that puts a bunch of these charges onto the plate, okay? So once those charges get built up, they just reach an equilibrium. So you have a certain amount of charge over here, and you don't have any more charge coming in, so you don't have any more electricity going out, so it's just constant. Basically, yeah, you just reach this equilibrium point, okay? Whereas, so that's why no electricity flows when you have just a DC voltage, okay? If you have an AC voltage that's sort of, changing up and down like this, what happens is that initially you're pushing some extra charges onto this side. So that pushes some charges off the other side. So it looks like electricity is flowing through there, right? Okay. And then the voltage goes down. So now that's pulling these charges off this side. So then that's pulling more charges back onto the other side. So you have this sort of this action where the charges are going on and off and on and off the one side, so that's causing them to go on and off the other side. So it seems like the electricity is going through. Yeah.
The one thing that really clarified capacitor and how it worked for me is it was explained like a diaphragm.
Uh-huh.
When you put a positive charge on it, it's pushing this way.
Yeah.
As soon as you take that positive charge off, it sucks back.
Yeah.
And it's pulling more charge back to it. So that's when it's recharging. And then positive push again. So when your AC goes up and down, it's just pushing that diaphragm. Exactly like a
Yeah.
speaker.
Yeah.
Back and forth.
Yeah, that's
It's
a great
just
analogy.
Pulling charge in and then pushing charge out.
Yeah.
Charge in and pushing.
That makes sense.
Yeah, and another thing about that I should point out is that just like with the diaphragm, nothing actually passes, the electricity does not actually pass through the capacitor. It just appears to be. So when you push charges on from the left, for instance, that pushes the charges off from the right-hand side, but they are different charges, right? So it might be the same amount of charge. So you get 5 electrons on the left, you lose 5 electrons from the right. So it seems like it's passing through, but it's actually it's different electrons that are moving off the right-hand side than the ones that came on the left-hand side, because you have this insulating layer. So the electricity never actually goes through this insulating barrier, but it appears to be. It behaves as if it were, even though it's being blocked. Okay? Yeah. So great questions. Other questions? Yeah.
When you were talking about what determines how long a capacitor can sit there with the charge, you were talking about some do manage to jump over. So is that
Yeah. So
they do
there's
actually cross, but that's not intentional? Or?
Right. There's a minute percentage that actually get across, but primarily, and like you said, that's not intentional. Primarily, it is due to this, charge, like charge, repelling like charge, and opposites attracting each other. Yeah. Yeah.
One thing with the blocking of the DC and pass through with the AC,
Mm-hmm.
do you have both of those currents going through the circuit at the same time? Is that a common thing? I guess that's what we were doing with the transmitter, right?
Right. So what you would have with the transmitter, for instance, is that you had a signal that looked something like this. So this is 0 volts down here. This is maybe 5 volts here. And so this signal has an AC component and a DC component. So the DC is the average voltage. So this would be like a 5 volt average voltage. So that would be about 5 volts there. And then the AC is this part that is moving and changing. So yeah, so this signal consists of partly DC and partly AC. And that's fairly common. Yeah. Yeah.
So is it just moving the baseline, or is it actually changing the waveform? Like, is it causing it to look different, or is it just moving the baseline up?
Oh, when you put the filtering capacitor in there?
Well, when you have DC and AC on there.
Oh, yeah. So the DC component is the average voltage. So if you were looking at the same signal that had a 0 DC component, it would have the same shape. It would just be centered around 0 volts.
So 5 volts is your constant. That's your DC.
That's the DC portion of the signal. Yeah. Yep. Good questions. Other questions? Okay. So that's what I wanted to say about capacitance. All right. So that's a little bit about capacitance. Like I said, we're going to have another lecture later on where we talk about capacitance in more depth, but that's a little bit about it today. So then, high current, there's not a whole lot of theory behind high current. Basically, In many applications, you only want to measure small amounts of current, but in certain circumstances, especially automotive applications, things like that, where you have more electricity flowing, you have to measure high current, and the meter can do that. So we've talked a little bit about frequency, a little about capacitance, and a little bit about high current and what those are. So let's talk a little bit about how we're going to measure those things with the multimeter in our lab, okay? All right. Okay, so this will take just a minute to come up. There we go. All right, so let's talk about frequency first. So the meter has a mode for measuring frequency. It is shown over here on the left-hand side of the meter where it says Hertz, HZ. So if you want to measure frequency with the meter, you just turn the dial into the frequency mode, and you put the leads with the black lead in the common hole, the red lead in this hole on the right that says V and omega, and then this will measure frequency. Okay, so we're going to measure a couple of different kinds of frequencies, or frequencies from a couple of different sources in our lab today. The first source is going to be coming out of the function generator. Okay, so you guys have all played around with the function generator before. We're going to use it today and try and figure out the maximum frequency that our meter can read. So we're going to hook the black lead of the meter to the black lead from the function generator, and then the red leads together, and then we're going to turn the function generator on, and the meter shows us the frequency that's coming out, right? So this says 2.36 or 2.37 kilohertz, okay? So we can move the function generator into different ranges using the buttons along the top of the generator, and then the meter will read the frequency that's coming out. So we are trying to find the maximum frequency that our meter can read. So you're just going to keep on increasing the frequency that's coming out of the function generator until you reach a number that says OL on the meter. Okay? If you go all the way up on the function generator and it never says OL on the meter, then you can just say it's higher than the highest the highest frequency that the generator can create. Yeah.
Will the DMM, will it switch over to megahertz and so forth, or is it?
Well, let's see.
I guess that's for us to find out, huh?
Yeah. Apparently it does. Yeah. So it'll go up into the megahertz range. So yeah. So you guys can try that out. Okay. So that's the first type of frequency that we're going to measure. After that, we're going to measure the frequency of the electricity in the wall. Okay? Do not plug the meter straight into the wall. All right? Yeah. I wish I didn't have to say it, but yeah, right. Yeah. Please don't. Okay, so you guys know that the electricity in the wall is high voltage, right? It's around 120 volts AC. It's plenty of voltage to hurt you, okay? Don't plug anything in there that's not supposed to go in there. What we're going to do is we're going to use a transformer like this. This takes the high voltage out of the wall and it brings it down to a lower voltage that's more like 15 or 20 volts. Okay, and that's not going to hurt you. So it'll lower the amplitude, lower the voltage, but it won't change the frequency. So you're going to plug the transformer into the wall. You're going to take a set of leads, just like the ones you use for the power supply or the meter, and you're going to plug those into the transformer. You're going to use the middle hole and one of the side holes, doesn't matter which one. And then you're going to, again, connect the black lead to the black lead, the red lead to the red lead, and then you're going to flip the transformer on. There's a little switch on the front. You just flip it up, turn it on, and then the meter should measure the frequency there. You don't want the two leads to be touching each other because that will create a short and it'll blow a fuse in the transformer. So if the little button on the back of the transformer pops out like that, that means that one of the circuit breakers blew, okay? These are resettable circuit breakers, so you can fix that, but it takes a minute or so for the circuit breaker to reset. So eventually it'll click, and then you can push it back in, and then you're good to go again, all right? So you can hook things up like this and measure the frequency, and then record that in your lab book. Okay. And then you're going to also hook up your function generator to a little LED, okay? And you're going to make the LED blink with the function generator. So you're going to turn the amplitude all the way down on the function generator, so it's creating almost no voltage. Then you're going to hook up the LED, and then you're slowly going to turn the amplitude up until you can see the light, until it just starts getting a little bit bright enough for you to see. Right? If you start with the amplitude way up, you can burn out the LED, and it can actually explode, which is not good. So you're going to start with the amplitude all the way down, and then slowly turn it up until you can see it. And then, when you can see it, you're going to hook the function generator to your meter and measure the frequency, and you're going to slowly you're going to start with the frequency on a very low setting, so it's maybe 1 hertz or so, one blink every second, and then you're going to slowly turn the frequency up until it looks like the LED is on constantly, okay? And you're going to find that threshold where you can just barely see it blinking, and you're going to record that. So that'll be the highest frequency that your eye can detect. So you're going to write down your value and then the highest frequency that your partner's eye can see. They're not always exactly the same. Okay. So that's what we're going to do for measuring frequency. Any questions about that? Okay. Cool. So then we're going to move on to measuring capacitance. Okay. So when we measure capacitance with the meter, we move the dial over into this section in the bottom right, where it is marked F. Okay? F stands for farads. Farads are the unit of capacitance, just like ohms are the unit for resistance and amps are the unit for current. Farads are the unit for capacitance. So we move the dial into the bottom right-hand corner to measure capacitance. Now, the tricky thing about measuring capacitance is that we don't use these leads that we've been using for all of our other measurements. Okay? We're not going to use these leads. What we're going to do instead is that we're going to plug the capacitors directly into these little slots that say LX and CX. Okay? So you're going to take the capacitor and you're just going to put one lead into one hole and the other lead into the other hole, and you have to push it down pretty firmly, okay? And then that is, that's the way that you're going to actually measure the capacitance. You might ask why we don't use the leads to measure the capacitance. And the reason is that if you have two long leads stretched out next to each other, really what's going on is that you have two pieces of metal next to each other separated by some insulating material, right? So these leads act like capacitors by themselves. So if you have the leads and then you have a capacitor on the end, you don't know whether you're measuring the value of the capacitor or the value of the leads themselves. So to avoid that, we remove the leads from the equation entirely, and we just use the short legs of the capacitor. Okay? Yeah?
For the electrolytic capacitors, would it matter which way you put it in there?
The meters have such low voltage that it doesn't really matter either way. Yeah. I believe that it says in the book to be careful and put them in with the positive side towards the positive, but in my experience, the meters are not going to blow them out. All right. So you're going to measure the value of the capacitor, and you're going to compare that to the value that's marked on the body of the capacitor. Okay? So some of these big capacitors have the number written right on there. So this one says 220 microfarads. Okay? So you can just read the value right off there. Some of the little capacitors, like this one, have the number written in a code. So this one says 2A224K, right? So we have to interpret what this code means. So let's talk a little bit about how we do that. So the important part of this is the 224K, right? And this works in a way that's similar to the resistor codes that we've talked about, the resistor color codes. Okay? So 224K is what we're looking at on that capacitor. So you remember with resistors, we would write down the first two digits, and then the third one was the number of zeros. It works the same way with capacitors. So you write down 2, 2, and then 4 zeros, and that's the number of picofarads that the capacitor has. Okay? So this is a 220,000 picofarad capacitor. And then the K is the tolerance. So just like the color band, the gold, silver, or blank band on the resistor indicated the tolerance, the letter at the end indicates the tolerance on the capacitor.
Is that 1,000 picofarad tolerance?
K, I believe, stands for 20%. So there is a sheet in your lab book that specifies exactly what those are, but I believe that's what that is. So if we wanted to convert this into microfarads like we see on our meter, we have to move the decimal point over, right? So this is, so if we want to convert to microfarads, that's moving the decimal point over 6 places, right? It's micro is 10 to the minus 6th, nano is 10 to the minus 9th, and pico is 10 to the minus 12th. So if we want to go from pico to micro, we have to move the decimal place over to the left 6 places. So this would be 0.225 microfarads. So that's what the body is telling us that it should be. So if we can compare that marked value to the value that we actually measured. So you say it's supposed to be 0.22 microfarads, but when we measure it, it says it's 0.221. So pretty close, right? So you're going to write down the value that you measure and also the value that is marked on the capacitor. Okay? So any questions about measuring capacitors? Okay. So then the last thing that we're going to do is we're going to measure DC current. So we've already measured low currents, right? You guys know how to do that. You remember that you plug the black lead into common, just like always, and then the red lead goes into one of the holes on the left when you're measuring current. So if you're measuring low currents, you plug it into the hole that says MA for milliamps. If you're measuring high currents, you plug it into this hole on the far left that says 10A for 10 amps. Measure up to 10 amps, right? So we'll start by measuring low currents. When we do that, we can put the dial in one of two settings. So we can put it here, and that's where it's marked 20 MA, so that can measure up to 20 milliamps. Or if we're measuring slightly more current, we could move it up to here where it says 200 M, to measure up to 200 milliamps, right? So when we're measuring low currents, we can use either of those two settings. When we're measuring high current, we have to move the red lead over to the far left-hand hole, like I said before, and then the dial can only be in one spot. It must be in this spot that says 10A, all right? So if you're measuring high currents, the dial must be there. What happens is that if you put it in this other spot, there's no indication to tell you that you're doing the wrong thing on the meter, but the reading that you get will be off by a factor of 10. It'll be 10 times too large, I believe. So there's no warning light that says you're doing something wrong. There's no other indication that tells you. All that happens is that you get a reading on the screen that's 10 times bigger than it should be. All right? So it's an easy mistake to make. So try and avoid that. Remember that when you're measuring high currents, the meter must be in this setting that says 10A. So if the lead is in the hole that says 10A, the meter must be in the setting that says 10A. All right? So any questions about that? Okay, so for the last part of the lab, you're going to do a few low current measurements and then a high current measurement using one of these lamp boards like we've used before. So you're going to measure the current through one of these lamps, okay? So that's all that I wanted to say about the lab. Any questions about that? Okay, so then, like I said, I will let me take roll and then I'll turn over the class to Professor Gary George and he will hand out some evaluations for you guys to fill out.